Sorry, it's unavoidable. I know I'm projecting my email, but it's very boring, I promise. Okay, where did I leave our slides? Okay. Genius. Okay, so we were talking about adiabatic processes, if you recall. Come on now. Yes, let's go, baby. Okay, so let's just get the old brain dust shook off. How did we get here? What are we talking about? Yeah, pressure, volume. What? Volume. Volume. Okay, good. We're now labeling things that I see on the screen. Lamp. I love lamp. You know what that's from? You know what that's from? Anchorman. I love lamp. Okay, your homework over the Thanksgiving break is to watch Anchorman and to report to me what I love lamp means. Okay, so we started with the ideal gas law. We used that to do something. What is it that we were trying to do in the first place? Convection. Convection, right? Yeah. So convection was a form of heating. And what we wanted to be able to say was how does the object, how does the thing go from a lower state to a higher state, right? And we said something about the fact that it was adiabatic. What does that mean? No change in heat, right? So the internal change in temperature has to be compensated with the change in density, right? Okay. And so we ended up with something that looks like this. Minus dP over P is equal to gamma dV over V. And generally speaking, if you ever have something of this form, you already know the solution. You can integrate it, but you can also just learn that this thing here, P times V, so whatever the thing is in front of here, gamma, right, is going to be equal to a constant. Okay. So for an adiabatic process, there's a relationship between the pressure and the volume. Of course, you can rewrite that volume in terms of the density if you care about it. And you would do that, for example, P over rho, right? And then you would get a constant. Let's use it. So how does T depend on P? All right, that's the thing that we maybe care about. We want to write an expression for how the temperature is changing with altitude. Well, we just used the ideal gas law to get rid of V, right? So you have this horrifying ideal gas law. How do I write the ideal gas law the bad way? PV equals nRT. Good. So let's get rid of V now. V is equal to nRT over P. Cool. We're geniuses, right? And if I want to take that to the power gamma, then I would just take that to the power gamma, right? And so therefore I have something like P times all of that garbage over P power gamma, right? And that's still going to be equal to a constant. So I don't necessarily care yet. But let me just go ahead and write this in terms of stuff that I do care about. I'm also going to be a little careful here. It's not nRT, it's nKT, depending on the size of the. If you use a little n, it's nR. Use a big n, it's. Okay, so we're almost there. So let's apply this everywhere. I have a -1 down here that I'm going to pull out. So this is P divided by P to the gamma. How do I write that? P divided by P to the gamma is number what? E to the gamma. Where's the E? These are just powers. You're just doing powers. What is the power of P here? 1. How do I write this statement?
E to the power of 1 minus gamma.
P to the power of 1 minus gamma. The minus means it's on the bottom, the gamma is on the bottom, right? 1. Good. Okay, so let's simplify that. Okay, so this is P 1 minus gamma, and the rest of this just gets normal gamma. Right? And K gamma T gamma. And that's constant, right? Now the cool thing is that that's a constant. So it's going to be the same in both, right? So if this is equal to a constant, then I can say that P 1 minus gamma T to the gamma must also be constant, right? Okay. And of course I can rearrange all that and differentiate it, get P by itself. The 1. Okay. So you can look at the one right above. So for example, you can rewrite this one in terms of this one with the P number. Right, this constant one. And this is what you end up with the dependence for gamma on PT. So it's something like PT, and I have this gamma divided by 1 minus gamma is a constant. And it's also you get it. Constant C. Okay. Okay. So this is pretty straightforward now. Because if I have something that equals a constant, then I can do a derivative. How do I know that I can do a derivative? Well, this thing here must have a contribution in PDT that gives you a constant by itself. Right? See how we can do that then? So if I take this to the other side, then I can just take dPdt on one side and the dPdt on the other side. And now I have a relationship between P. What? It's just low. Yeah, it's well, we take the derivative here, so we get another version. This comes out, the dBdt. That's just imagine that was like x, e to x. X comes down, and then you get x minus 1, and this becomes gamma minus 1. And then you get this. And if you rearrange that, you see that it is E over T. So this is telling us how the pressure is changing with temperature. Okay. Here's the best part. Oh God. All right, so now we want the part that we care about, which is how does the pressure change with altitude. Okay. So we already have here dPdZ. And so now we have this thing that we just found, dPdt. Right? So we plug that piece in there. And we have something like dTdZ, right? We said this was in hydrostatic equilibrium, so we already know what this piece is. It's minus rho g. The reason that the pressure changes has only to do with minus rho g. But now we have an ability to find out how the temperature changes with altitude just by taking this, putting it on the side. Right? So now I have something like dTdZ, and I have all of this here. Well, Then I just have this. Make sense? The mu comes from the definition of the ideal gas law, which we use N. The mu is the mean molecular mass. I said that I was going to be more careful about that, and I wasn't careful at all. So it's up here, like this. What?
Why is it usually?
Because I assume that it's the same gas, which isn't a great assumption if you're using an atmosphere, right? But like if you had an atmosphere that's fully made of hydrogen, then the only thing you care about is how many hydrogens you have, right? Not how many hydrogens you have of a certain unique mass, which is what you really should. Okay. Is this integrable? I'm glad.
Times the.
Yeah, it's pretty straightforward. We did all that work to get something that is basically linear, right? Okay. But it's trivial. You have to have some starting place, and then it gets colder as you go up. Okay. We make some assumptions, right? G needs to not change very much, right? Because if G is basically a constant with altitude, then this is fine. You don't have to integrate G. And it's got to be basically what it was at the surface. That's the first one. We also got to say that Z, wherever we're considering this over, is small compared to the radius of the planet. If that's not true, then you can do this, right? And then the rest of it, it's just as Z. You give a constant. Okay. We call this is the dry adiabatic lapse rate. That's just a bunch of words in a row. But what that means is that this is how we expect the temperature to change if it is adiabatic. Okay. And so we're going to look at a couple different examples of whether or not the atmosphere is less or more steep. Okay. And one thing that you want to keep in mind about the words steep, okay, when we're thinking about derivatives, let's imagine that this is temperature and this is altitude. Okay. Let's say my dry adiabatic lapse rate is a line starting at some value and then going downwards. Okay. Starts at some T0 downwards. Okay. So what does a more steep line look like? More vertical, right? So this would be the steeper one. And what does a more shallow line look like? More horizontal. Good. Okay. Now counterintuitively, which has a higher scale height? What's that? The vertical. Does it? What does scale height mean again? The meaning, not the. Yeah, 1/3 of whatever it is. So it was talking about an exponential process. And we said, how high you go before producing 1/e. Right? Okay. So now let's think about that again. Which of these is reducing most quickly? What? Right. The more shallow scale height. So just need to be careful when we think about the words shallow versus steep. Steep means quick decline, right? But unfortunately, the idea that we use of like quick decline is actually a very large scale height. So it's not changing very rapidly. Whereas a shallow scale height, something that seems kind of smooth and easy to go through, is changing more rapidly. What?
And they said more speed, goes faster.
Oh no, more steep, like when we think of the word steep. When we think of the word steep, we think go quickly. But in fact, that the use of the word steep here is misleading. Right? Because it certainly is steep, but that represents very little change with altitude. As opposed to what we would expect, which is like when you fall, you're going quickly. Okay. All right, so I just want to draw conclusions that were draw the distinction there in the words that we use, right? So we're going to talk a little bit about some of what that actually looks like when we look at the atmospheric profile, right? But what I want to just point out is in a location, let's say you find a place where the temperature is varying linearly with z, okay? It's approaching this form, the dashed line. Then you think, oh, that part is convection. The heat is being transported there by convection, right? So let's imagine, right? Let's imagine that you do in fact have an exponential. What does an exponential look like on top? Let's do the normal one really quick. What does the normal exponential look like? Starts at some value like 1, and then goes what? Goes up. Straight up? Curves like that, right? Okay, so now if we're going up and to the left, we're reducing by the exponential. So we start here with that one, right? Okay, so let's think about that now. You start at some value, and then you go up. You see? So in this section here, you are more or less shallow than the dry adiabatic glass, right? More shallow. You're losing temperature faster. In this section, you are more or less shallow than the dry adiabatic. It's actually about the same. So even though it's physically shifted over, it's the rate that we're looking at. And I know there's curvature in there, but I'm not a good one. And then from here to here, shallow. Same. Good use of all S words. Okay, so where does convection occur? Okay, we have 1 vote for shallow and steep. 20% of the votes cast. Varies linearly with the Z. So when the temperature profile is the same as the adiabatic lapse rate, that is changing only with Z, then you have convection. So it's same. You see that? That's what we found. We found this is the definition of convection. Because when we said things about convection, we said, well, same goes up. The temperature changes in a certain way, but it doesn't exchange with the environment. This section here, the temperature is changing too quickly for convection to be non-adiabatic or to be adiabatic. So therefore, this fluid cannot be convected. Let's show it on the atmosphere. Oh god, that came out really good, huh? Okay. So this says altitude, this is height, and this is the temperature. Okay. And what you're looking at here is a temperature profile. It's actually a temperature rate. Okay. And so what you're looking at here is the simplest atmosphere with CO2. This is a model of the quantities for CO2. And for CO2, you have gamma equals 11 ninths, which don't worry about it, you won't have to calculate it, you can just find it. And then it'll get high enough and it'll run out of energy and it'll decline to 9/7, but heading north to here. So up to here, 11 ninths is fine. And you can actually see that in the dT/dz. So this is observational data here, the red line from Vera, which does retrievals of thermal emission in the atmosphere. And you know, you look at those two and you say, okay, well, where does convection happen? This is a little confusing because it doesn't look like this, right? I am not plotting T by Z. I'm plotting K per distance on one, which is like the T/dz on the bottom, and on the top, the resultant altitude. Plotting lapse rate here versus exactly. So where they're close together, where this roughly equals this, the lapse rate matches what we expect for. I didn't leave it up on the board. Damn. Okay, let me just go back. I'll show you what it means. Oh, there you go. Okay. So take this thing. Oh, go one more time. Take this thing, TDZ, lapse rate. You can measure it. You can measure how the temperature is changing. And you find out where is it close to this thing. Doesn't have a bunch of numbers. But it is a number, right? So for example, when you're thinking about an exponential temperature, right? And you're going to plot it, maybe you don't want to plot temperature. Right? Because you have it exponential over here, and maybe you have some local results over there. So you might just plot the lapse rate here. And that will better show you, because it's taking into account the fact that it's changing, right? It should be constant in some places. And where it's constant, it will be convective. Or where it's this constant. Okay, so let's go back to that picture. All right, so where did you say it was? Where? Yeah, so where? here, right? Up to here, and then you stop convecting at about 30 kilometers. Is that it? Where else? Yeah, right here, you have another convection. Good, and that's what this beautiful picture shows. Okay. There are cloud layers. This is the vertical structure of Venus's atmosphere. They mostly lie outside of the convection zones. So what I'm showing you here is where the clouds are. This one, the first cloud deck, happens right after the convection. So you bring up, now it's not water, right? It's hydrogen. Yeah. It's sulfuric acid, that's the word I was looking for. So you're bringing up sulfuric acid in droplets. Because it's fucking hot there. Okay, so sulfuric acid's a liquid. Okay, it's mixed in as a vapor. It rises through the convection zone. And then as it makes it to the top of the convection zone, it's deposited. Right? So remember, now it's cooling off enough that it's going to begin to sink down. And it's cooled off enough that they begin to condense into clouds. And maybe you have clouds up here, and finally it gets warm enough, you start to have a little convection as well. And so now you convect those clouds up, the sulfuric acid, and then you build another cloud deck. Now, why this one forms, I don't exactly remember. But lowest layer, thinnest, most opaque. Below it, clouds on Venus. That make sense? Okay, let's see where we're headed next. Yeah, let's talk about this really quickly. So now we're actually looking at the temperature profile as a function of altitude, and I have adjusted the altitude significantly. But we were just looking at the bottom of the troposphere there, starting at something like 700 degrees Kelvin, and then going all the way back to balmy, that's like little, basically, near 170 at 100 kilometers. You get a thermal inversion, so that just means where the temperature stops going down, it's over. That inversion, so we use the word pause to mean that something has changed. So for example, the tropopause would be the location where the temperature inverts and you have a bifurcation between what's called the troposphere and the thermosphere. The thermosphere, not surprisingly, hot sphere, right? We're not very good at any of this stuff. On Earth, you have something called the hydropause. So that's the part of the atmosphere where water vapor is rising, and then condenses out. And what you'll notice is that if you were to map the water vapor as a function of altitude, okay, it would look like this. So the total density is gonna go down because you're going up in altitude. So you might have something like this, right? Okay, and so this is the H2O density. But the mixing ratio, that is to say how many particles of water you find as a function of all the other particles in a given volume, right? So as the density goes down, the total number of particles go down, and the mixing ratio is a constant, right? Because it's well mixed in the atmosphere. Until you get to the hyperpause, and it condenses out, and all of a sudden it drops to zero. And similarly, the density of water drops to zero, right? So one of these, this would be the ppm, and this would be like the centimeters minus 3 number. And that's the hydropause. And so we use the word pause just to talk about the location where you have a shift like that. The thermosphere on Mars, or on Venus, has a substantial day-night difference up here, right? And one of the major reasons for that is that Venus's day is as long as it's here. So on one side, it's getting absolutely blasted by sunlight, and on the other side, it's just chilling. if it were more rapidly spinning, then that hot air would physically be taken to the night side, where it would have the opportunity to cool. As opposed to what currently happens is that you have very hot air on one side, very cold air on the other. So you set up a pressure system. Because necessarily this hot air is going to have a different pressure than the cold air, and so you're going to send jets from the day side to the night side. And we see evidence of this with the Japanese spacecraft that's there. That makes sense? Okay. Okay. Let's talk about the Earth's atmosphere. That's the only one you care about, right? So, where are the locations here that one gets convection? Yeah, first one, right? Because that kind of looks linear. Right? And I'm not gonna hold a gun to your say that is that exactly linear, right? That's close enough. That when it's linear like that, decreasing upwards, you could make a good argument for convection as good. So that's convected there. Is it convected here? Between the tropopause and the stratus, so the tropopause and the stratopause. No, definitely not. Right? That is linear, but it's in the wrong direction. Right? So that certainly could not be convected. And in fact, the necessary conditions for convection, which is where you have a hot gas, low down, and it rises, wouldn't be satisfied here. You have a hot gas up, and that's in its happy place, right? It's happy to be there. It's not going to go here. All being fine. Good. What about from the stratopause to the menopause? Yeah, it kind of looks linear again, right? Now the question, and the one that you would have the complete right to ask is, well, Prismani, what's your mixture of gas and the gamma that you use? Because that's going to define the slope of the linearity, right? Because if the necessary slope is like this and it's too steep, you won't have convection. Okay. So now we know how to read a plot like this. We're looking for places like that, and of course, details are very important, but I'm not going to piss you off. Above the tropopause, you have stratospheric increase caused by the ultraviolet absorption of UV radiation by ozone. So that is what creates the stratopause here. And you were not alive for this, but there used to be this thing called hairspray. We didn't use it to make very big hairs. Some guys do too, well, myself personally. But you would have like big hair, and it would release something called CFCs, and that turns out super bad for ozone. So you can destroy the ozone layer. Didn't know that. That's interesting.
So that why they stopped producing it.
Yeah. So now you can still get hair. They just don't have CFC. And that wasn't primary form of CFC. That's happened. Okay. Fine. Here's Jupiter's upper atmosphere. Is there convection here? Where? Exactly right, right? So that looks really linear. The difficulty, of course, with Jupiter is that there's no surface. So you have to create a zero altitude. And that's a choice, right? Because, like, what do you do? Start from empty space? Well, where does empty space start? Like, you need to create a pressure. And so what we do is we set zero equal to the P of 1 bar. Remember, 1 bar is our current atmospheric pressure and temperature, right? So we set that here. And you can see that there's a tropopause that happens basically right above it. The pressure levels are over here on the right, sorry. So we're getting smaller and smaller pressure levels. These are, I believe, decades as you go up. So this is P to the power 1 over, 1 100th of bar. So each one of these, this is 1/10 of a bar, 1/100th of a bar, so on and so forth. So each one of these is a day. You guys know how the magnitude system works? Yeah, it's the same. Good. And the reason that we do that, sometimes you'll see modeling and they won't show you the altitude. They'll only show you the pressure. Because pressure in a lot of ways is more important. Even though we physically interpret something like the altitude, the pressure is the thing that's changing. And that's the reason why you have atmospheric dynamics in the first place, right? So for example, here at the microbar or the millibar, the microbar level, this is the location where an incoming asteroid or a piece of dust that is barreling through the atmosphere is going to get enough heat to burn up. And that just happens to be true at the microbar pressure level, regardless of the planning room. So like everyone has a very common pressure altitude at which things burn up. And for Jupiter, it's 400 above that one bar, but the Earth is like 170. And so that's why we might use on the right hand side of the pressure to understand the similarity. Okay. Convective troposphere, and then you have like an isothermal stratometasphere thing, and then it gets hot and it heads off into the okay. Did you know how we got those? Remember? About the probe called Galileo. Okay, yeah, oh, there's some clouds. So there's your line, very linear. You get ammonia sulfide and ammonia clouds, one above the other, and that's only due to their condensation. Okay, before I get into atmospheric escape, I think it makes sense to talk about circulation. So I'm going to skip over. Unless you guys want to do escape first. Let's do circulation. Okay, let's keep talking about structure and then we'll talk about escape as a whole. Okay, so we're going to talk about Earth as a planet. Can you believe we saw that? Hey, we'll just do a couple of the highlights about Earth. We'll talk about the circulation. We need to describe something called the Having cells, which I've alluded to before. And then we'll talk about the greenhouse effects and how life has a distinct impact on the atmospheric dynamics and also geology as well. Right? Which one's our pilot? What are the features that we see about Earth versus the Australian planet? Yeah, ocean. There's like clouds, right? And the left-hand side, is this a real picture of Venus? What's wrong with this picture? Coloring? No, not exactly the coloring. Or almost right. It's missing clouds, right? You can't see the surface. So that is what the surface looks like in radar. We've never seen the surface as a whole in the visible. Okay. All right. Here's the stats about the Earth. It's big. Of course, my favorite part is that these pieces here, right? We just turn them into Earth radii. We don't never have to memorize them. What's the moment of inertia? Do you remember that? Yeah, it is 1/3, but what does that mean? What is the moment of inertia? How differentiated, right? And what were the things that we used to mark how differentiated something was?
So it's more differentiated.
Good. You remember what kind of fractions meant different types of bodies? Five, you mean 0.4? Yes. 2 or 5 was undifferentiated, right? 0.4 is undifferentiated. And the maximum differentiation we ever got was like a shell, like a weird shell of mass at the very edge and nothing. Do you remember how big that was? Yeah, 0.667, right? Or 2/3. So, so this is pretty okay, right? We're differentiating. Is that surprising? No, of course not. We know we're differentiated. We've seen the pictures of the core, we have earthquakes, right? Albedo, is that surprising? No. Yeah, ocean's very dark, right? So even though we have clouds and like on a very cloudy snowball Earth, you can get that up to like 0.6, 0.7. But for the most part, the blueness of the ocean is a real heat sink. Effective temperature, that's fun. Is that what we feel on a day-to-day basis? Anyone know how to convert that into Celsius? Minus 273, right? So, uh-oh. Is it minus degrees on Earth? What's happening? We would all be dead. If not. Be frozen, dead. So maybe we should pollute more. Okay, so there's something that drags us. It's not even one. How fucking stupid are we? The definition of the AU is not the AU. That's okay. We turned out that we didn't have all the digits when we first did it, and we got better at measuring. Orbital eccentricity is about 1%. That's how long the day is. That's how long the year is. That's the main thing. This is big, but that's a guess. I don't think we've seen Jupiter yet. I think I have the numbers on how big the magnetic field there is, but just remember this is about half a guess. Okay, let's talk about Hadley circulation. George Hadley was a dude. He wanted to describe something that has been seen for a very long time. So I'm going to do a really bad approximation of this right now. But you like my art skills, right? Okay, so if you are a seafaring person, that is to say, you want to make your money bringing goods from one place to another. You have the East Coast. No, that's Florida. And you have Europe. That's France. Okay. That's Europe. Okay. Just calm down. Okay. Now they're not the right latitudes here. So just imagine that it's tilted. I didn't draw it very good. So you want to go from Lisbon, which is here, and you need to deliver goods to Europe. Right? And you have a sailboat that's 1700. So which way do you go? If you were a plane, yeah, if you were a plane, you do this. Why would you do that? Exactly, yeah, that's the shortest path, right? But interestingly enough, they, depending on where they were going, up or down, they might take their boat and sail it down and then sail. And on the return journey, they wouldn't do that. On the return journey, they would do something like this. They found that there's really good wind. It was always blowing in this region, and then up here it would blow in the other direction. And in this little section here, there'd be doldrums. That's really dangerous if you're a boat trying to go across the Atlantic Ocean. Doldrums just means no wind, right? So you'd have wind going this way, and you'd have wind going this way. These are called, not surprisingly, trade winds. And they're not perfect, but they're pretty consistent. And across the ocean, they would find the striping. They would find wind going like this, wind going like that, wind going like this, wind going like that. Right? Like, that's so weird. What the fuck is going on? Oh, I don't know. I'm just bringing, goods and services from point A to point B. we'll ignore the fact that the slave trade. Okay. So Hadley was like, I'm very interested in understanding how the atmosphere creates these very consistent winds across the ocean. So he said warm air is less dense than cold air. Is that true? Okay, so we made a bubble. Okay, so it rises. It's got to go somewhere. It's got to sink. Right? So we just found out, of course, that we have convection. No one doubts that. Right? So he said, here is the edge of the planet, super well drawn. That's the equator. What's the hottest place on the surface according to, I know that was a couple weeks ago now, when we were doing like, how does the temperature change as a function of latitude on the surface if you ignore the atmosphere?
Like in the equator.
Yeah, it's like the equator, it's the point that's like 28%, right? So let's say this is the hottest. And let's start a little bubble. Okay? Here's my bubble. Top bubble. And now it goes where? What? Rises, right? Yeah, sorry, this is not going to be to scale. The curvature of the earth. Okay, let's be calm for a second, but let's just imagine. So now our hot bubble is nice and cool. And it's probably expanded in size. But it can't stay there. Right? Because it's getting pushed by the bubble underneath it. So now where does it go? So does it just go right back down over the other bubble? Or it can't, because it's getting pushed below from the bubble. It's got to push to the side, right? So he said, okay, let's push it to the side. Arbitrary. It's going to choose. Okay, so it's cooling, and then eventually, okay, it's nice and cool, and now it is cooler than surrounding, so that's it. Good. And now it's this nice cool little bubble. And this is cooler than this is, right? So now it starts taking heat, but it's still getting pressed. So now it has two choices. It's got to be pushed aside, right? Left or right, right? Okay, so if it goes this way, it's going to heat up, and it's going to finish the cycle. If it goes this way, then what happens? Keeps cooling. Okay, well, that's really interesting. So it keeps cooling. Okay. It just cools forever. So interestingly enough, yes, it is true that this is hotter than this is, but you still have some amount of heat. So it falls down, it's still going to heat up. It needs to rise. Right? You don't simply just have these two fountains and then no circulation for the rest of the atmosphere. It's still hot enough that you get evaporation. It just takes time. So this cell might be whiter, but eventually you get a bubble here and it rises again. And the cycle repeats. Okay, so now you have something like that up here. And then he has two choices. Okay? And he cools down as it goes over, and then he runs into his friend bubble. These are now, have I described why this happens yet? No. Okay. So he said, yeah, there's that difference in incidence angle. There should be north-south circulation with warm air at high elevation flowing towards the poles and cooler air's surface flowing towards the equator. Right? I think his very first approximation didn't do it locally. It said like that, you know, and then it must sink in the northern hemisphere like that. That's not. So let's see that in a second. So that was the first approximation, right? It's wrong. So the trade winds, not explained by that. So the reason that you have to think about the fact the whole planet is rotating, and you have a Coriolis effect, right? So as I go from. Okay. So let's say I start moving, how does the Coriolis effect work, by the way, in the northern hemisphere? Good, yeah, so let's see if we can use that to understand the Coriolis effect in the northern hemisphere. So. You understand the Coriolis effect? You're on a rotating body, you throw something straight, here's a curve. Right? Okay, so this is the equator. I'm only gonna look at the northern hemisphere right now, okay? That's more north. So remember that at the equator, we are moving the fastest. So the relative velocity, the relative angular rotation, right, is the same for the northern hemisphere, but the relative angular linear velocity changes. As I move towards the very pole, I would no longer be moving, just rotating, right? So here I'm going the fastest and I go slower. So you can imagine that I have a horizontal component that decreases this. That's pretty good drawing. See that work for them. Okay, so now I want to go up. Okay. And that's my intended goal. What do I appear to do? Great. Splendid. Cannonball. Standing at the equator, I shoot it back. Where does it appear to? Okay, so I'm shooting at this speed plus this speed. Right? Yeah, so when by the time that I get up here, the Earth is only moving that much. So the difference by the time that I make it far up is the difference between them. Like that. Necessarily. Right? And at first, you're going to notice very little of it because the ground is moving like you're moving. But as the ground slows down, it becomes more apparent that you have more speed. Okay. So that's the first one. Let's go down now. Still shooting a cannon. But now I start with very little velocity. Direction like. Yeah, wide left. Same difference, right? But now over here, the ground moves away from me. So the ground moves faster than I did. So I appear to be back. Okay. Deflection. Okay. And if I go this way, remember that I'm drawing on a flat board. It's not quite accurate. Right? Because the Earth is curved, even though it looks like I'm doing this, it's really this. Right? Remember that a straight line on the map is a curved line. So in fact, we can never get away from the fact that let's say you pick a single latitude. Then you're still gonna have Coriolis because you're differentially rotating. So you still end up, even though you have something like this, it still ends up. You're always turning to the right. And similarly, if you're going backwards, you're turning to the right. So now we have everything that we need in order to understand the trade winds. Okay. So let me demonstrate that that's all we need. Let's start with this branch here. Okay. Does it affect the rising motion? Yeah, so let's look at the surface. Okay. Here's the surface of the earth, and you're going up. Which direction? Let's say the earth's rotating this way. What? Yeah, the block appears to be left behind, right? And as you sink, right, you appear to be. Yeah, so we also have the Coriolis effect in 3 dimensions, right? And now we're beginning to see, oh, shit, look, it's being dragged in the direction of motion. So different parts are going to feel pushing and pulling, right? And we can begin to understand why they are rotating, which would look like this stack above the floor. Okay, so that's the conceptual part. Here's how the velocity looks. Okay, so you can derive this if you want by looking at the terms in the Coriolis force. In particular, you want to look at the speed, right? The rotational speed as a function of your latitude. So this just means 2 pi r, that's the radius, the circumference in a day. And of course, the cosine theta tells you how far up, right? So here you're going the full equator. Here, let's say it's 30 degrees. Up here, you'd be going 0. And so that tells you how far your physical distance you're going in a day, right? That's not a difficult definition, right? Okay, good. So at the equator, the Earth's rotational speed is almost half a kilometer per second. At 45 degrees, it's down to a third of a kilometer per second. At 75 degrees, it's about a tenth of a kilometer per second, and 0. Okay. So now we can draw on a globe. It's okay, it's not great. This is, trying to put all these pieces together. So in the northern hemisphere, we said it turns to the right, right? And that's that warm high altitude flow. That's this piece here, but now it's moving away from the equator and it's turning, right? Okay. And as warm air is pushed north or south, it finds some moving in slower air and it moves out of the normally rotating mass, right? Underneath, the return flow goes the other direction, right? So it's trying to go this way, it's deflected, and this is happening at the surface. Okay. The core, this is this one. Between cooling and turning, the high altitude flow only makes it about 30 degrees. And then it sinks. And that's where you get your first hazard sun. Now, is that 30 degrees? No. Did I try my list? Not really. So you can take advantage of the difference in speeds and solar heating to form another sun. So you can, we can start at the other end, think about how cold it is at the poles, and invert this process, right? And there's a large cell called the polar cell, right? So this is the first one, the Hadley cell. This one is the polar cell. And there's one in between that has the opposite rotation. So this rotates like this rotates the opposite direction. Okay. And that's the Faro cell. I can draw that here if you want. These rotate in the same direction, rotates in the opposite direction. This one rotated with this one. And we have 1, 2, 3, 4, 5, 6. 6 suns. Okay. The number of cells you have here is a function of your rotation. If you're rotating quickly, you get more. What is rotating fast in the solar system? Jupiter is going real fast. How fast is it rotating? 10 hours. The Coriolis force there is humongous. Do you know how many Hadley cells it has? Hadley cells? How many things? Like more than 20. How many does Mars have? That's rude. Maybe one. We'll see.
Oh, yeah, let's see.
Yeah, so Mars is really thin atmosphere, right? So it doesn't have a lot of the same effects, or the atmosphere's thin. It's not very energetic and it's fog. So Mars has a very unique atmosphere. Okay. That's the atmosphere. At some times of the year, it does this. Because it takes literally that long for this air to cool off, sink in the poles, come back to the equator in order to get hot enough to rise. And it has a 2 Hadley cell. And then, weirdly enough, at some points in the year, the subsolar point gets low enough. Right? Because one of the things that Mars does is that it gets closer to the sun during southern summer. And the subsolar point moves such that you have 1 Hadley cell for the whole planet.
Mars such a silly goose.
Okay. That's it. Cool.
Hopefully one of them can do it.
I regret nothing. So this is the the northern hemisphere prevailing wind system. So here is your super high res too. Really good image. Here's your equator, and there are doldrums at the equator. So you don't want to like travel on the equator. Here you get circulation that goes up. This is the high altitude. It gets, it's hot, and then it sinks at about 30 degrees. And these are the trade winds that are sweeping the northeast, and they're called the northeast trades. And then you have the prevailing westerlies, and then you have the polar easterlies. And that just tells you which direction they're coming from, not which direction they're going to. So the prevailing westerlies come from the west and go to the east in a very normal and not confusing way. So if you want to go west, you would use the easterlies or the trades. If you want to go east, you would use the westerlies. Cool, right? Very easy to understand. Just be glad you don't like run both these things. And here's your sun. Right, hot, cold, sink. This is the equator. 30. Right, and we might say to ourselves, well, it's not exactly like what I thought it would be, and that's mostly because the whole fluid is right. It is a fluid, so you still have to do fluid dynamics. Okay. You can also see the shape of the cells there. There's a polar cell that has a little cap. Sometimes you get, depending on what planet you're looking at, you might get a little hat. I'd like to wear a little hat. Because over here, so these are pressure systems, high and low, low. And you have this material is hot, rising, then it cools, and it's probably moist. And now you wear a nice little hat with clouds. And then it drops the moisture there, the clouds form there, and then it's cold and so the atmosphere itself falls out and then sweeps across the surface. Okay, there's a lot of evidence to suggest that Columbus understood this. So on his way to murder and rape and pillage, he took advantage of some science. And this is his path. I kind of did it. That was kind of close. I went a little, I should have gone lower. So the westerlies are up and away to go home, and the trade winds here are down to the left. Oh. Yeah. Had we like figured this out without the Coriolis effect, it would be 100 years before we found the Coriolis effect by Guy and Gaspar and Coriolis. So the mathematics to understand the rotation or the force, the fictitious force that arrives from the rotation of the reference frame is something that just hadn't been figured out yet. So this Coriolis force is like that centrifugal force, but it's using an accelerating reference frame. Okay. So here, you have the angular velocity of the reference frame and your own velocity within it. It's not real. You know, if you were watching from space, you would see normal motion, right? If you could take this thing off. So Venus is a great example. Slowest rotator of all the planets. Most of the circulation is only north-south. Right, super hot at the poles, and it's as hot at night as it is during the day. The whole planet, despite the fact that on the night side, it doesn't see the sun for 300 some or 170 days. I forget exactly how long it is. It's still 700 degrees. And that has everything to do with the fact that circulation is north-south. It's not east-west. Basically, no Coriolis. The habitability of Venus is entirely due to the fact that the whole atmosphere, the whole is greenhouse gas. So you have to remove 89 atmospheres of greenhouse gas. And then you have to add an ocean worth of water. And then you have to get the plates to subduct. So you can restart the carbon cycle. And then it could be happening. So it's expensive. Wouldn't recommend it for the off season. And so, people are talking about Venus for a long time, and we want to go back there. We want to grab some of the surface and find out about the geology. The greenhouse effect is obviously famous. We'll talk about that in detail. We talk about the Earth in a few seconds. We think, and this is really hard to prove, that Venus started off with the same ingredients. So it's a giant assumption that the Earth had water, that Venus had water, because we have one. So after the surface cooled, we assume that water was delivered to both of these planets. And it's, of course, for reasons that we'll talk about, not possible to prove. But must be a surface. So we think the water, we talked about the fact that we turn comet water and asteroid water. We think that there's no reason why that wouldn't happen in Venus. So it probably was delivered to ocean. If plate tectonics are normal with water, the hydrated crust, then that probably happened to Venus, right? And it's only through the runaway greenhouse effect that you turn Venus into unlivable healthy. Okay. I think that's all I can give you today. I'm sorry that we started a little late, but for Tuesday's class, let's finish up this discussion. I'll show you a little bit more about, the atmospheric escape. So we'll talk about the atmosphere's structure, and then we'll be done. We'll talk really briefly, after Thanksgiving about Jupiter, Saturn, Neptune, and Uranus, just like their composition in terms of all of these things. And then we can decide whether we want to do formation theories, formation models, chemical models. Basically have like 1 week left. So that'll be it. You have a homework, and then I'll give you 1 more. That's 1 or 2 less than I would have liked. Questions, comments? Okay, break.
How much homework do you like?
It's due the Tuesday after Thanksgiving.